So, we are now in the last leg of discussion on suspension modeling. So, in the previous lecture we went through in some detail trying to look at suspension viscosity, and what we finally concluded is that the calculation of suspension viscosity gives us a particle stress which takes the form where the particle stress depends on the imposed rate of strain, and there is a viscosity which is a function of volume fraction, and if you were to also account for thermal fluctuation, it would be also a function of Peclet number. And in the last lecture what we realized is that mu obviously takes a form that is I think mu fluid is what we have been writing, mu s is 1 plus 5 half phi, and then when you start working out the next order terms, the coefficient is crucially reliant on the nature of the linear flow. You do a steady simple shear flow, you get one particular value of the coefficient. You do a planar extensional flow, you get another value of the coefficient. So, the nature of the background linear flow or shearing behavior that you have, that is actually determining what would be the next correction to your viscosity. And the reason that happens is because it is playing a role in terms of determining what is the probability of finding a neighbor, because this particular term is a pair interaction term, the order phi square term. And so, the order phi square term is coming about by knowing what is the probability of finding a neighbor at a particular distance away from the reference particle. Now, how your neighbors are distributed, that is crucially reliant on the nature of the flow. Every flow will have its own distribution of particles, and so that is the reason why the calculation as it goes to higher order in volume fraction, it becomes crucially reliant on the shearing behavior. And then we also saw that what actually takes up when you go to concentrated suspension, in which case the volume fraction diverges at a maximum packing, and there are various empirical forms which allow you to get a nature for mu of phi. Now, this, as I had mentioned earlier, this gives a description of the fluid as what we would call as a quasi Newtonian fluid. So, I am saying quasi Newtonian because the stress is dependent on the rate of strain in a manner which is similar to how we understand Newtonian fluids. The difference is there is a volume fraction dependent viscosity here. Now, if the volume fraction was a constant, it was not a function of spatial coordinate, then mu is also a constant. It takes a number that is different from the solvent value, but it is also a constant. Now, what would determine what is the distribution of volume fraction, which basically comes from how are the particles distributed. So, should the viscosity, which is a function of the volume fraction, also be a spatial function? So, which would require you to ask the question that if I were to study the conservation of particle concentration and write down an equation for the volume fraction, there is going to be a change in the volume fraction, the local volume fraction, due to advection, but there will also be a change that would occur due to diffusion. So, in total you could write this as a divergence of some flux is equal to 0, where this particular flux can be written as u phi minus d del phi. Okay, that is an equation you are writing for the particle concentration. So, this is going to determine how the particles are going to actually get distributed and how would the volume fraction change. So, this brings about the next question, which is regarding the diffusion of particles. How would the particles actually diffuse? Because if there was no diffusion, then it is just merely going to be an advection process, that the particles are purely just going to follow the respective trajectories as given by the background velocity, and you will have the particle concentration field evolving due to that. So, this if you are thinking of the dilute limit, you can think of this as a dilute Brownian suspension. So, there is the particle. So, this goes back to the Langevin description that we spoke at some point in the past, that the particle is being constantly bombarded by solvent molecules, and the consequence is that the external force can be written in terms of a mean component that depends on the particle velocity plus a fluctuation, where we assumed that this particular fluctuation is a zero mean Gaussian. What is that we assumed? White noise, a delta correlated process, right. This is what we had basically considered, that the consequence of collision with all the solvent molecules surrounding this massive sphere leads to this irregular motion of the spherical particle, and you get what is known as Brownian motion. So, as an illustration, if you were to tag this particular particle, this is a simulation of the Langevin equation. So, this is a particle that is moving under the action of that white noise, and what you observe is this kind of an irregular behavior. So, if you observe this for a long time, you are going to observe that the distance that it actually spreads out, that distance is going to behave as square root dt, right. This is how it is going to actually move around. So, this is the case for dilute Brownian suspension. Now, we have already gotten acquainted with interaction. So, the question is, what would happen if this particular sphere that we were trying to study was also interacting with its neighboring spheres? So, as I said, when you are imagining this picture of a big particle trying to move in a soup of solvent molecules surrounding it, it is experiencing collision with solvent molecules, where there is a bias of collision in the direction of motion compared to the other directions over the surface of the sphere, and that leads to this aspect of that the acceleration of the particle is balanced by the Stokes drag term and the fluctuation. Now, if there was also surrounding particles which were present, not just the solvent molecules, then I need to do this random walk in a crowd of like particles. There are obviously solvent molecules which is responsible for my Brownian motion, but then I am trying to do this in a space where I see neighbors around. So, you have an ability to do this wiggly motion. That wiggly motion or that basically fluctuating behavior is due to all the solvent molecules constantly bombarding. But you are not in free space, you are surrounded by other particles around. So, when you are surrounded by other particles, you are trying to do this diffusive behavior, but you have to do this diffusive behavior as if you are in a cage. You are in a cage surrounded by all other particles. So, each of these particles which I have not colored, they are also doing the same, but if I am tracking this particular tagged particle, it is doing its random motion, it is doing its Brownian motion, but while it is present in a crowd of similar particles. So, what do you think is going to happen to its diffusion? Would its diffusion actually increase, or would its diffusivity increase, or should it decrease? What do you think is going to, I mean, just before you think of anything further, how do you think of what its diffusivity is going to be? Should it diffuse more or should it diffuse less? It should diffuse less, right? Because it is surrounded by, so there is a constraint, right? You are not able to freely diffuse. You are surrounded by many other particles, so you are kind of trapped, and because you are trapped, you have less mobility to move, And now we know this word mobility in our context is a technical word. It is not just an English language word. So, the diffusivity is kT, the average mobility. The single particle mobility is, what is the single particle mobility? Right. So, the diffusion that we studied, where we wrote down the Stokes-Einstein relation, this is the general Stokes-Einstein relation, where the diffusivity of an object is related to its mobility. Now, if you do a single particle problem, the mobility is inverse of 6 pi mu a, and it is an isotropic quantity. But when you are doing this in a crowded environment, the mobility is an average of all possible configuration of your neighbors. So, now you can go back to the kind of calculations we were trying out, right. When you think of two spheres which are falling, you know how to basically study the interaction problem, and you know how to actually calculate what would be the mobility in such a problem. So, you get less mobile as you have these neighbors. So, your diffusivity is going to go down as the volume fraction starts to increase. So, you are not as mobile as before. Now, this is an example of diffusion where the volume fraction of both the tagged and the untagged particle is the same, right. If you look at this particular picture, there is no change in the total volume fraction here. You have a uniform distribution. I am basically tracking one such particle, which is why the term that is used is self diffusion. You are tagging or you are tracking one particular particle, and you are trying to compute what would be ddt of this. We learnt about mean square displacement, and we learned that mean square displacement for the 1D problem that we did, mean square displacement went as, what was mean square displacement in the 1D problem for long time? 2 dt, right. When we solved the Langevin equation and found the position of the particle, and we obtained the mean square displacement for a single degree for single translational coordinate, it went as 2 dt. So, you can measure this, you can measure the coordinate of the tagged particle and find the ensemble average dyadic quantity xx, take a time derivative of that, half of that is going to basically give you the component of the diffusion tensor. This is self diffusion. But you can also measure diffusivity by measuring through a region what is the flux, which would be this quantity. That is an Eulerian approach. This is a Lagrangian approach that you have. This would be an Eulerian approach. I draw a particular slice in the domain, and I am basically measuring what is the flux of particle crossing that location, and that gives me a measure also of diffusivity. Now, you can ask the question, are they the same? Now, this picture that I have on the left side is a picture where I have all the particles distributed in this room. So, imagine again, think of the students in a classroom. If the classroom was completely packed, where all the students are spread out uniformly, and I choose one particular student and I am trying to track how that student is basically trying to make his or her way out of the classroom. That is a motion of a tagged object, and if it was where the person was moving purely due to thermal fluctuations, then they are going to do their wiggly motion, they will jiggle their way through in this crowd where all their neighbors are also present. Measuring the flux is where you create a concentration inhomogeneity, and then you try to find out what would be the flux of particle as it tries to homogenize. Because what does diffusion do? Diffusion is basically a process by which it will homogenize without the action of any external force, it will homogenize the field. So, what are the examples by which you can create inhomogeneity? You can use any external force like electric field. Let us say the particles were responding to electric field, you turned on the electric field, all the particles migrated according to the direction of the electric field, and then you turn off the knob, you switch it off. Now, when you have switched it off, you are basically starting out at t equals to 0, a scenario where all the particles are accumulated in one direction, and then they are going to spread. Now, when they are going to spread, this is something that is basically due to gradients. So, that is why the term this is gradient diffusion. So, when you are going to solve for a concentration equation, the diffusivity that you have is a gradient diffusivity, whereas when you are making measurements for the position of a tagged particle, then you are measuring self diffusivity. In the isolated particle limit, when phi goes to 0, they are going to become equal. When there is no interaction, when you do not have any interaction, then what you call as self diffusion is the same as the diffusivity that appears in the particle concentration evolution. But when you have interaction, they are completely different, they are not equal. So, this is an important point which you need to keep in mind when you are trying to model suspensions. If you are trying to write down an evolution equation for concentration field, you have spread, I mean it is not exactly suspension, but imagine that you have spread perfume in one corner of the room. So, those molecules which are basically the fragrant ones, they are going to spread, they are spreading due to a concentration gradient in the problem, and that diffusion process is basically being driven by what we are calling as gradient diffusion. Now, if you were to replace those molecules by bigger particles which we are talking about here, the suspension particles, they are going to interact with each other while they try to homogenize the concentration field. So, when interaction is important, gradient diffusion and self diffusion are not going to be the same, because self is when you are tagging one single. So, you see the two pictures are very different. On the left, when you are talking about self diffusion, yes, it is interacting, but it is interacting and trying to break away from a cage. Whereas on the right side, when you are talking about the gradient diffusion, you have created an inhomogeneity in concentration field, and that concentration field is basically spreading out, and that spreading out of the concentration field is driven by the amount of gradient diffusivity that you have in the problem. So, these are ideas which starts to kick in, that is traditionally not discussed when you are thinking of diffusion of other scalar fields. Because here interaction is such an important thing, as you can see that even for something as straightforward as diffusivity, you have quite a different picture depending on what is your question. Is your question tagging, like you make one of the particles fluorescent and you are tagging that, or you are tracking that tagged particle, that fluorescent particle, you are basically tracking it in the problem. Now, that fluorescent particle cannot penetrate through its neighbors. So, obviously, it has a hindered motion. So, that hindered behavior or that hindered diffusion is going to be captured by self diffusion. Instead, if you were to say that I have particles kept in one particular region and then I remove the barrier, they are going to spread out. They are basically spreading out due to your gradient diffusivity. So, this is something that becomes important when you are discussing Brownian suspension that are concentrated, where particle interactions are important. So, a lot of problems in engineering systems would be dealing with Brownian suspensions. In food industry, pharmaceutical industry, there are a lot of scenarios where you are dealing with particulate matter that are Brownian in nature. They could be few hundreds of nanometers to maximum maybe tens of microns, where if they are concentrated, if you are trying to model their behavior, you need to account for the concentration dependent diffusivity. Now, the diffusivity scales inversely with the particle size. We know that, right? There is obviously a function of volume fraction, but it scales with the particle size. Now, if you are looking at particles which are massive, so by massive I mean particles which are not few hundreds of nanometers, particles which are tens of microns or hundreds of microns. The previous example, what we had probably in mind would be like, let us say, fat globules. But right now I am thinking of big colloidal particles, few hundred microns in size, polystyrene beads. There, if you were to compute the diffusivity, we did this exercise in previous lectures, the diffusivity would be almost 10 to the power 14, 10 to the power 15 units. What are the units? Meter square per second. Very small diffusivity, which means if you are trying to calculate the Peclet number, the Peclet number being defined in terms of a shear rate as gamma dot A square by the diffusivity. The Peclet number can be extremely high, which means there should be practically no Brownian motion. If you remember the original experiment of Robert Brown, that as the particle size increases, the Brownian behavior or the disorderly behavior starts to go down. So, on the right, what you are seeing here are a set of experiments, again done for particles for which diffusivity is very low, the Peclet number is significantly high, and the experiment that you are doing is what is known as an oscillatory shear experiment. So, imagine you have the top plate moving with a prescribed shear rate, that is gamma naught cos omega t. So, you have fixed a shear rate. Instead of doing a steady shear experiment, you are doing an oscillatory shear experiment. So, there is a back and forth motion of the plate, a very standard protocol usually used in viscometric measurements. Now, the difference between the two videos, as I will play, is the shear rate, the amplitude is varied, keeping everything else fixed. Now, in the top video, you are looking at this motion of these particles. There are few which are also out of plane. So, this is a full 3D image, video rather. And what do you observe? That the particles are executing this back and forth motion. This is Reynolds based on the particle is extremely small. The particle Stokes number is extremely small, which means by reversibility of Stokes flow, the particles will do back and forth. The particles will do back and forth behavior, and they will come back to where they were originally. Now, if you increase the strain amplitude, you see something like this. The only change that you have done is increasing the strain amplitude. For low strain amplitude, it is doing this back and forth behavior. For high strain amplitude, it is doing a behavior that is quite reminiscent of Brownian motion. If you didn't know anything else, you would have thought this is basically a reconstruction of an experiment done by Robert Brown or Perrin, that you are actually observing this Brownian motion behavior. Yes.
Is the faster version of this or
higher strain amplitude? So, what you are doing is you are basically increasing this. You are doing an oscillatory experiment. What you are doing is you are increasing the amplitude of the forcing. So, if you imagine that one way to increase the amplitude is that if the velocity, so the top plate is moving with a velocity u, so the top plate velocity is some u naught cos omega t. So, you are increasing that u naught, keeping everything else fixed, you are increasing that amplitude of oscillation for the top plate, and this is the behavior that you observe. Now, this is quite puzzling because there is no thermal nature to this behavior, even though it appears like a thermal problem. This is completely athermal. Whenever the Peclet number is very large, you would say the system is athermal. Temperature is not playing any role in the system. So, if temperature is not playing any role in the system, how do you basically end up getting this kind of a disorderly behavior? So, if you first ask the question purely from a dimensional argument, So, if you first ask this question from a dimensional argument, you know kT by 6 pi mu A has the dimension of diffusivity. What would be another way of getting something that is a function of the variables that are there in the problem and has dimensions of diffusivity? So, go back to this problem. Obviously, you are looking at this problem at the scale of a single particle, right. So, the particle has a length scale A, and then you have an oscillatory shear flow. Temperature is playing no role, obviously you have viscosity of the fluid. So, how do I get a diffusivity, something that has dimensions of diffusivity using this? Diffusivity has dimensions of meter square per second. So, I need something which has meter square per second. So, one way I can construct meter square per second is I can take the size of the particle squared, that gives me a meter square, and per second I can take the shear rate, that has dimensions of diffusivity. So, actually what you would have is gamma dot A square times some function of volume fraction, right. So, now you may ask the question that okay, this is dimensionally making sense, but what the heck is going on, like where is this coming from? Just by increasing the shear rate, why is this kind of a behavior happening? So, if you go back to our discussion when we were trying to understand about interactions, we did a little bit of two sphere interaction when we were trying to think about the viscosity calculation. We were writing down the relative velocity. So, we were writing something like that the relative velocity between the two spheres had a form which was some gamma infinity dot r minus a r hat plus b delta minus r hat. So, if you were tracking these two spheres, you would get nice trajectories of how these two spheres are moving with respect to each other. Now, if you have a third sphere in the problem, a 3 sphere problem, this becomes chaotic. This is no longer an integrable system, this becomes a chaotic system. You can study this in different ways as a first level approximation. You can think of this as stresslets interacting with each other. Now, why is that an important conclusion? Why is that something that we are trying to think of, the chaotic aspect? Because once the particle trajectories become chaotic, you will never be able to retrace your path. So, when you are doing this kind of when you are trying to do this exercise, here the particles are doing a back and forth motion. You go forward, you come backward. Like you reverse your motion, the particles are exactly tracing it. When the system goes into a chaotic state, this is no longer possible. That is the essence of a chaotic system, that it is extremely sensitive to your initial conditions. You will not be able to exactly trace your path. If you think that going forward, the plate going forward is running your movie in time forward, and then reversing the plate is running the movie backward in time, they are not going to lie on top of each other if the system is chaotic. You take two spheres, coming back to what you know from Newtonian mechanics, you take two spheres and you basically make them collide. They are going to bounce and they will execute a certain post collision trajectory based on how they are bouncing. Now, if you run the movie backwards, which means you exactly give them the post collisional velocities and run it backwards, they are going to retrace the path. So, that's the point I was trying to make, that when you think of two billiard balls which are colliding with each other with no other physics that is going on, purely a Newtonian mechanics problem, the two billiards ball problem, you can exactly retrace the path if you reverse their velocities, right. Now, instead of 2, if you do this exercise with 4, if you do this with 5, the system is basically going to not be guaranteed in being regular. There can be possibility of chaotic behavior, and when you are not doing precise initial conditions, which means when you are having these 4 billiard balls interacting with each other, you can get a highly chaotic event. Now, there the force transmission is during collision. In hydrodynamics, the force transmission is from a distance. You do not need them to make contact. Each of these spheres, they have a velocity field that is going as order 1 over r square. So, every one is generating a velocity field that is order 1 over r square. So, when you have this many body interaction problem, it becomes a chaotic system. So, when you are repeating this over many time cycles, you will not be able to retrace your initial motion. So, with the passage of time, you are going to increasingly see a behavior that is a diffusive behavior. The word diffusion here is used in not the sense of molecular diffusion. The word diffusion is here used in a sense that you are going to get a mean square displacement that is going to grow linearly in time with a diffusivity that scales as gamma dot a square. So, there is a critical shear rate after which the system will no longer be retracing its path, it will become chaotic. So, the underlying equations of motion are Stokes' flow, we are not changing that. The underlying equations of motion basically has reversible dynamics, that is the idea of Stokes' flow, right. When you have several particles interacting via this Stokes' flow velocity field, the Stokesian velocity field, the many body interaction problem becomes chaotic for the particles. And so, when you are tracking these particles, you are not going to see any kind of retracing of their trajectory, and they are going to move around as if they were under the action of thermal fluctuations. There are no thermal effects here, there is no thermal fluctuations in the problem, temperature is not relevant in this problem. This is purely a diffusion like behavior that is driven by shearing. And the reason also why I am drawing this distinction, because the diffusivity that we talk about, the diffusion process we are talking about, is something that is an equilibrium process. Here there is a shearing, so it is a completely out of equilibrium process. So this out of equilibrium is a completely non-equilibrium process where you see this diffusive behavior, that where the diffusivity depends on the amount by which you are shearing it. So that is why this is a very interesting idea, and this is an idea which seems initially very perplexing. It appears perplexing because we are so used to thinking of Stokes flow basically offering reversible dynamics, that we then find it puzzling that why do you actually have, in absence of thermal fluctuations, particles executing a disorderly behavior. But then when you take a step back and you think a little bit more, there are many particles here interacting with their long range flow fields, and so it is not surprising that this leads to a system where the particle dynamics or the particle trajectories becomes a chaotic dynamical system. Now this one of the earliest experiment which captured some of this came from the work of Eckstein, and subsequently there were many others who picked on this and tried to rationalize what was going on. But in a similar direction, the shear mediated interaction, because you have to understand the interaction is mediated by the shear. If there was no shear, there was no interaction. This is an athermal system. In the previous thermal system, here there is an interaction between the spheres which is basically mediated by the thermal fluctuations. Each of these particles are trying to undergo Brownian motion, but then they are impeded by the surrounding neighbors. But in the one that we are looking at here, there is no such thing. So the degree of random motion is mediated by shear. So this takes us to the last part of this particular discussion, which is something that comes from a set of experiments which were initially not targeted for this. This was so this is an excerpt from a very nice article by Andy Akrivos in the Journal of Rheology, which is a transcript of his Bingham Medal lecture, and again I would encourage you to read this to also get historical account of how this evolved. So one of the things which he was interested in was properly quantifying the variation of viscosity for different fluids with volume fraction, because there was a lot of spread that people were reporting in the literature. We have always been talking about the viscosity aspect. In that context, with one of his PhD students, he had a task where there was a company for which he was working who wanted the viscosity of cold slurry to be measured. The company, this is a pure engineering question. There is a material, you come back, you tell me what is the viscosity of this material. Now as I said, I mean, to measure viscosity you need to shear the sample. You cannot, it is not like measuring density, which you can do in a static state. To measure viscosity you need to shear the sample, you need to set it into motion, and then from the calculation of either the shear stress or the torsion or the torque, from that you try to infer what is the viscosity. That is the way by which you make measurements of viscosity, and fairly standard and straightforward kind of measurements. So he has this kind of an experimental setup that is shown on the left, and he wants to measure the viscosity of cold slurry. Now cold slurry obviously is a messy material, and you want to quickly make measurements of viscosity before it all sediments out, because the particulate matter in cold slurry is heavy. So if you let it set, if you let it stay, it is going to fall down. So before it sediments out, assuming that the sedimentation speed is not very large, you want to quickly make measurements of the torque that is acting and thus find out what is the viscosity. So the part that I have highlighted here you want to basically, they were interested in that they were heavier than the suspending liquid and had a chance to settle out. Preliminary experiments suggested that whereas the coal was settling at low shear rates, it could be resuspended by increasing the shear, which means when you are looking at this on a long time scale, obviously the coal is, the fine particles are basically sedimenting. But then if you increase the rotation rate, it seems to get resuspended. And they even tried this, if you read the next part which is not highlighted, that they turned it off, let everything settle down. So it completely got cleared out and it had to settle down. Then when you turn it up, it got resuspended by shearing it. So what does this tell us? This tells us that there is a gravitational flux which is trying to pull the particle down, but there is also something competing that is balancing it. Now, if you recall, we had a similar discussion during going through Einstein's calculation of diffusivity, and there the point came from molecular diffusion. Now, these are particles which are fairly large, there is no molecular diffusion that is there. So, when he tried this out, molecular diffusion is completely ruled out, and when you increase the shear rate, you see that there is a certain distribution of particle concentration. Not all the particles are settling down at the bottom of the container. There is a certain layer thickness over which they are getting suspended, where there seems to be something else balancing the gravitational flux. And what was done also subsequently by another set of experiments by Leon and Leal, and there were also experiments earlier than this by others, where they observed in a setup like channel flow, the velocity field was not parabolic. The velocity field was a little blunt towards the center. So there are these two kinds of observations. One is the observation from the experiment done by Akrivos, where you are seeing there is something else that is balancing the gravitational flux, and then there are the set of experiments which were done by others in the past, and then what I am showing here is Leon and Leal, where you are observing that the channel flow velocity profile has a more plug like nature towards the center line rather than being a perfect parabola. So with all of that comes a question that is the concentration of particle uniform in these kind of scenarios. So if you go to the experiment of a channel flow kind of a setup, this is a more recent experiment where you have more sophisticated means of actually tracking particle concentrations. What you are observing that at the entrance you have a nearly uniform concentration of particle, but then if you are measuring this at the outlet, the concentration becomes inhomogeneous. There is a likelihood of finding more particles near the center line. So this is the center line than near the walls. So particle seems to go and accumulate towards the center, and this was again done by making sure that the Reynolds number of the particles is very small. So what we discussed in few lectures back regarding inertial migration, we spoke about the lift forces, and we said that when you account for finite Reynolds number, particles can migrate across streamlines. That is not at play here, that is not working in these problems, because here the Reynolds number for the at the scale of the particle is very small. So these are concentrated Stokesian problems, whereas what we have discussed earlier, those were single particle finite Reynolds problem or non-zero Reynolds problem. So you shouldn't be thinking in terms of that inertial migration, so that is ruled out. So the idea that came from Akrivos and then many others from that group, and there were also others working on that, is that there is a flux that depends on gradients of shear rates. When you have non-uniform shear flows, a lot of discussion we have had in this course was on uniform shear flows, a plate that is moving and it creates a linear shear flow. But a channel flow, on the contrary, is a problem where the shear rate is not a constant. The shear rate is maximum at the walls and goes to 0 at the center line. So, when you have non-uniform shear flows, the gradient of shear rate creates a particle flux. This is basically the phenomenological way by which Akrivos, Leighton Akrivos and Phillips, many others basically argued that there is a shear induced migration that is occurring in this system. So, what is the shear induced migration? You have a concentrated system. This concentrated system, when it is basically being sheared, the interaction of these particles mediated by the shear is responsible for the particles to move from regions of high shear rate to regions of low shear rate. So, this is where things were for a period of time, and gradually, I mean, again, whatever I am going to finally finish with, these are still mostly ideas which are in progress. Some of it we know quite well, some of it which we do not know that well, is where we are kind of converging to the idea that all of these things need to be understood from a single entity, which is the particle stress. If you remember, there was a particle stress which we wrote down when we were trying to work out viscosity using the idea of stresslet. So, the particle stress at that point in time, when we were discussing the idea of viscosity, we only focused on the shear part. We did not discuss anything about the normal part of that particular stress. We were only saying, okay, what is the correction to the shear stress and how does it depend on the volume fraction. So, now if you think of this system, there is a concentrated suspension that is basically being sheared. As you are trying to shear this, the particles are also going to exert a certain pressure on the boundaries. Now, why are they exerting this pressure? This exertion of pressure is basically happening due to the particles colliding with themselves and also colliding with the wall. It is very similar in idea to what you would observe as osmotic pressure. If you have a U-shaped manometer, if you have a solution, the free surface level would coincide. We all know that, right? In a hydrostatic state, it should coincide. Now, if you put a semi-permeable membrane, where here you have a solution and here you have pure solvent. Let us say this is water and this is water plus sugar. This is semi-permeable, which means water can go through this membrane, but sugar cannot cross. What will happen? You will have osmosis in this problem, and then eventually you would have the level come down, because you would have more solvent molecules going to the other side, increase the volume on the other side, and then whatever is the deficit here, that is your osmotic pressure. So, this is basically what we know in terms of what is going on in solutions. In the same way, when you are thinking this for suspensions, you can actually make very nice measurements, and these are, again, as I am emphasizing, you can also see with the years of these references, these are very modern. Even as of now, these are quite modern approaches of understanding the problem. Instead of the top plate basically being a no penetration plate, imagine there was a porous plate. So, if there is a porous plate, then you can choose the size of the pore such that the fluid can go through it, but the particles cannot go through it. So, pore size is smaller than the particle size. So, when you are going to actually do this shearing experiment, the fluid is going to rush out, particles can't rush out. So, these are known as, so you can do this experiment what is known as a pressure imposed rheology. All the other experiments that I discussed, those are shear imposed rheology. Right now you would be applying a fixed pressure and then do the experiment rather than doing a shear imposed rheology. So, doing that, what you observe is you are measuring a particle pressure or a normal stress. There is a force with which it is getting pushed, and you observe with volume fraction the particle stress is increasing. Now, here the particle stress is scaled by the shear stress. Whatever is your tau, you are scaling. So, you can do this experiment either as a shear imposed rheology experiment or as a pressure imposed rheology experiment, where you have a porous top surface, you hold it fixed, not let it move, and then do the measurement, or you let it move up and down based on whatever is the particle pressure. So, this normal stress difference, I mean, there are different ways by which now you can calculate, and why I am saying this is a difference is, if you calculate what is the normal stress in the gradient direction. So, this is the y component of the particle stress, this is the x component of the particle stress, and similarly if you measure sigma y minus sigma z. Now, in a simple shear experiment of a Newtonian fluid, the pressure field is isotropic. So, there are no normal stress differences. If you do this experiment of a simple shear of a Newtonian fluid, which is to say that you have no particles present in the problem, you will have no normal stress differences. But when you do it for suspensions, you will actually find that there are normal stress differences that are coming up, and this basically comes about because you are breaking the symmetry that is there in the problem. It could be breaking symmetry in terms of the particle surface being rough, or there are many particles interacting with each other. So, this is what you are seeing here. There is a single sphere, and then these are trajectories of the second sphere with respect to this sphere. Now, if you were to draw a line joining these two spheres, if I track the length of this line, so there is like a dumbbell whose rod can change its length, right. So, what you see here, if you remember, we wrote down the relative velocity expression once again, gamma infinity dot r minus a of r hat plus b of delta minus r hat dotted with E infinity dot r. If you solve this for a simple shear flow, these are the particle pair trajectories with reference to one of the spheres. So, this length that I have drawn here, what will happen to this length as the second sphere approaches? It is going to shrink or compress, and then it is going to get stretched. So, this problem basically has a symmetry, which means there is a compressive direction and then it is going to get extended, there is an extensile direction. When you have something that breaks that symmetry, let us say roughness or charges, then that breaking of symmetry is going to lead to normal stresses in the problem. You can also break that symmetry by having a third particle interacting with these two particles. So, this is the key idea. So, here what you are seeing once again is the experimental data for these normal stresses, and finally what you see here is the normal stress differences N1 and N2 being plotted as a function of volume fraction. And again, there is a lot of spread that are there in terms of experiments. There are some very little theory, but these are things which we still don't know sufficiently well. There are careful experiments, there are also careful simulations that are done and continue to be done, formulated, but this is basically where modeling suspensions is there. So, I have just written down here one last equation which is basically trying to say what is the particle concentration equation. This is motivated by a pioneering paper by Knott and Brady that tries to write down this equation by saying that particle concentration has this usual advection part. The rate of change of concentration or rate of change of volume fraction is driven by a combination of advection and a flux, and the flux is the divergence of particle stress, and the particle stress has a component that comes from the viscous part, and there is another part which is the normal stress part. And this normal stress part, you can further write it down into a thermal part which is isotropic and a hydrodynamic part which is not isotropic. So, the key point is that the normal stresses due to the hydrodynamic interactions are anisotropic. And if there is something that you can immediately argue from the linearity of Stokes flow, that the normal stresses due to hydrodynamic interaction should be linear in the shear rate. This is the point we have been making from lecture 1, that if you have to argue how should the normal stresses scale with the shear rate, with all the complications being there, the normal stresses should be linear on the shear rate. Now, if the divergence of the normal stress drives the particle flux, that is equivalent to there being a gradient of shear rate, which means that if you have a non-uniform shear flow, which was the picture I had drawn earlier, particles are going to migrate towards regions of low shear rate. So, which kind of explains some of these pictures, because the center of a channel is 0 shear rate or low shear rate. The walls have high shear rate, which means particles are going to migrate towards the center line. So, this shear induced migration incorporated into the model with your thermal diffusion part, all of that together is somewhere where we are in terms of modeling these systems. There is still a lot to go, there is a lot to be done, but this actually kind of concludes regarding how we go about viewing suspension as a continuum. Okay. So, with that I will close this lecture, and that is all. Yeah, thank you.